Right. So, hello everybody, I'm Théo Gayoux, I'm a second year PhD student, and today I'm going to talk about studying clustering dark energy with a new simulation called Nefertiti. So the context is obviously dark energy. So we want to understand what is the nature of dark energy, because today we are living in an accelerated phase of the expansion of the universe, meaning that there is this weird and exotic component called dark energy. So today, one of the best descriptions of the universe is made by the standard cosmological model, the lambda CDM, where lambda stands for dark energy and CDM for cold dark matter. So this is a very good description of our universe, but there are some assumptions. For example, the density, dark energy density is a constant in space and time. And this model is very good to describe the observation, but there are some issues. For example, it is only empirical. There are some discrepancies between the theory and the observation, and there are some cosmological tensions. That's why people are trying to improve this model by adding some layers of complexity. So, for example, they add time dependence in the dark energy density. Those models are called WCDM. And basically, the lambda CDM and WCDM model can be well represented by the Ramses cosmological simulation. And there is another class of model called clustering dark energy, in which the density has a time and space dependence. So we can basically form dark energy halos. And this can be done with Nefertiti. This can be studied with a Nefertiti simulation. So what it does is basically solve the fluid equation in an expanding background to model the evolution of the dark energy density. And the goal is to study the nonlinear regime, so very late time. So this code is basically based on Ramses. So it uses the fluid approximation to model the dark energy, and as well as the adaptive mesh refinement to solve high density to resolve high density regions. So my job in this simulation was to first set up the initial condition and do some post-processing analysis of the outputs. And so at the moment, there is no tool to actually analyze the output of the simulation. So I thought about YT because YT can handle the Ramses outputs. So we're thinking about doing, for example, some halo finding, some cool visualization, some merger trees, some clump finder, and volume rendering. And then we can do some theoretical predictions for like surveys like Euclid. So what has been done so far, so what I did so far is to, so basically the outputs are not the density field, but the over density field. So at the moment, what I did is that I just replace the hydro field in the Ramses front end by this over density field. And then I add by hand some derived field to compute the density on the grid and the mass and so on. And this is, for example, some movies about the projected dark energy density field. It's the evolution with cosmic time, and this is the projected particle plot that models the dark matter density field. So yeah, my objective for this week is to learn as much as I can about YT and how to handle a hydrodynamic field, and as well about parallelism, since because we at some point we will do a big simulation and we'll need to parallelize everything, and do some cool plots for future paper because the code is not public yet. And I also want to provide to the future Nefertiti users some YT code snippets for post-processing analysis. And yeah. So if you have any recommendation and ideas, I'm very glad to discuss it. Thank you very much for your attention.
Yeah, you can just hit stop.